Hey guys, Mr. McKinney here, just wrapping up our lesson on Riemann sums. We're going to look at a couple of old AP questions that we've modified slightly. So the broken thermos problem, we've got a table of values that models time and the temperature of I'll just read it. The temperature of my coffee at time t is modeled by a strictly decreasing twice differentiable function c, where c of t is measured in degrees Fahrenheit and t is measured in minutes. At time t equals 0, the temperature of the coffee is 105 degrees Fahrenheit. The coffee cools for 30 minutes. Beginning at time t equals 0, the values of c of t at selected times t for the first 20 minutes are given in the table above. So basically, we've got a table that models time and the temperature of our coffee as c. Twice differentiable is not telling you that this is the second derivative. That just means that this function could be differentiated twice. You could take the first derivative and the second derivative. That's a common adjective that you'll see on the AP exam. It just means you can take the derivative twice. All right. So this first problem we're going to look at, it says use a left Riemann sum with the 4 subintervals indicated by the data in the table to approximate the integral from 0 to 20 of c of t dt. And then does this approximation over or underestimate that integral? Explaining my reasoning. Keep in mind that on the previous slide, we said that the temperature is strictly decreasing. That's going to be important in answering this question. So a left Riemann sum, we're doing rectangles. We want 4 rectangles. The distance between these first 2 is 4. The distance between these next 2 is 5, 6, and then 5. So for each of my rectangles, and we can draw a quick scatter plot over here. So we've got 0, 4, 9, 15, 20. So 4, 9, 15, 20. And then we're going down. So we're starting at 105, and then we go down just a little bit, and then down a little bit more, and then we start dropping off a little bit quicker. So I want a left Riemann sum with 4 intervals. So I'm going to draw rectangles coming from the left. All right, so the work that I want to show to find the integral from 0 to 20 of c of t dt. So we're trying to show the work to find the value of this definite integral of c of t dt. So we're just showing how we calculated each of these 4 rectangles. So rectangle 1, 2, 3, and 4. Each rectangle, again, for area is just going to be base times height. So we just need to show what we're using to find the base and the height. Now I already subtracted them up here, but on the AP exam it would be better if we show how we're calculating that base. So we'd do 4 minus 0 times the height on the left, which is 105.0, plus, and then 9 minus 4 times the height that's on the left, which is 104.1, plus, and then 15 minus 9 times the height that's on the left, which is 100.8, plus 20 minus 15 times the height that's on the left, which is 91.9. I think you would probably be fine if you did that subtraction and just showed this, where you've already done the subtraction. I think that this would be okay. It's better if you show where it came from, but as far as my understanding, this would be okay. Now, again, depending on whether you're on the calculator portion or not, you would either type it into your calculator and hit enter, or you could just box it in the unsimplified version. So if I did simplify this, I would get 2004.8. If we think about the units for t was in minutes, and the units for c of t was in degrees. So if I multiply minutes times degrees, I'm going to get like degrees Fahrenheit minutes, which doesn't make a whole lot of sense. So on the actual AP exam, they would ask a different question, which I'll show you in a second. But for now, this would be our answer. Now let's explain the second part. So does this approximation over or underestimate that actual definite integral? So we don't even need to think about this picture necessarily. Just think about the fact that C is decreasing. So if we do a left sum on a decreasing function, let's look at the simplest version possible. So the simplest decreasing function that I can think of is a linear function. And if I'm doing a left Riemann sum, then all of these rectangles are going to be above the function. So this is going to be an overestimate. And to explain your reasoning, you would just say that this is an overestimate because we did a left Riemann sum of a decreasing function. You don't have to explain a whole lot. Like explaining your reasoning, all you have to say is that we did a left Riemann sum of a decreasing function. So make sure you reference whether it's a left or right sum, and make sure you reference whether the function was increasing or decreasing. So when you're justifying an over or an underestimate, talk about which type of sum you did and whether it was an increasing or decreasing function. Or if we were dealing with a trapezoid, you would talk about whether it was concave up or concave down. Now let's take this problem a little bit further. So this is what you would actually see on the AP exam because the units will make more sense here. So instead of just the definite integral, we've got this 1 over 20 out front, and it says that the average temperature is 1 over 20 times this integral. Use a left Riemann sum with the 4 subintervals indicated to approximate this. So we already calculated the value using a left Riemann sum of the definite integral, and we got 2004.8. Our units didn't really make sense because they were degrees Fahrenheit per minute. But they will make sense when we take into account this 1 over 20 because we're going from 0 to 20. This is our time. So this is really 1 over 20 minutes times 2004.8 degrees Fahrenheit times minutes. Now our minutes can cancel out, and my average temperature, which makes sense, would be 100.24 degrees Fahrenheit. So on the AP exam, if they gave me degrees like this, they would probably have something like this where you were doing average temperature. We haven't covered average value yet, which is why I introduced it with the other version of this problem, this one, because I wanted to focus on actually creating the sums. But I wanted to follow up because this is what it would actually look like on the AP exam. Let's get one more question in here. So this last one has to do with koalas eating some eucalyptus leaves. So the rate of consumption of eucalyptus leaves in Australia by koalas is given by E of t is equal to 1.898 times e to the power of 0.0153 t, where e is measured in billions of grams of leaves per year, and t is measured in years from the beginning of 2015. Use the trapezoid rule with 4 equal subdivisions to estimate the integral from 5 to 7 of e of t dt. Interpret your answer in the context of the problem. So we're definitely going to be using our calculator for this one. Now you can do all the work in the calculator, or you can make a table of values and then write everything out. I'll kind of show it both ways. So we want to go from 5 to 7. We want to break it up into 4 intervals. So 5 to 7 is a distance of 2 divided into 4 intervals. Each interval is only a half big, or 0.5 wide. So we're going to go from 5 to 5.5, from 5.5 to 6, from 6 to 6.5, and from 6.5 to 7. And at each point, we're going to draw a trapezoid. So we're going to do 1/2 times the 2 bases, heights added together, times the height or the distance in between the 2 endpoints. So for example, for the first interval, it would look something like this. B1, B2 are the heights at 5 and 5.5. And then the height of this trapezoid is actually kind of like the width or the base. Now again, I'm going to let my calculator do it for me. If I'm on a problem like this is on the calculator portion of the exam. So let's look at, we're going to need 5 values. So my t values are going to be 5, 5.5, 6, 6.5, and 7. And I'm going to let my calculator do it for me. So just put your equation into y1. Now on your calculator, you use x instead of t. And then on the main screen, you can just do y1 of 5, and then y1 of 5.5, and so on, down to y1 of 7. And you can find these values that way. So you'd get like 2.0488, and then you'd get 2.0646, and so on. I'm not going to fill this whole table out. It's just a bunch of calculator button pressing. Now, to estimate this, we're going to do 4 different trapezoids. So each trapezoid is going to be 1/2. Now, in this case, the height of the trapezoid, which is how far apart the time intervals are, is always going to be 1/2. So I'm going to add together 2 things, but at the end of it, I'm going to multiply by 0.5 because that's how far apart they are. So for this first one, I would be doing whatever I get when I put in y1 of 5. So basically e of 5 plus e of 5.5. And then I'd have 1/2 times e of 5.5 plus e of 6 times 0.5 plus 1/2 times e of 6 plus e of 6.5 times 0.5 plus 1/2 times e of 6.5 plus e of 7. And again, I'm going to do this all on the calculator. Like, you could write it out, but you don't really need to. You need to show what you're calculating, and then you need to write out the answer. And again, on my calculator, I can do it all at one time. So on my calculator, I would be typing like 0.5 times y1 of 5 plus y1 of 5.5 times 0.5 plus, and I do the same thing 4 times. Now, if I do all these calculations on my calculator, I should get 4.161151223 or something like that. So let's interpret my answer in the context of the problem. So E was a rate. First of all, if I integrate a rate, if I go up from a rate, we're going to be at an amount because it's like amount and then a rate, and then below that would be a rate of a rate. So to go down levels, you're taking the derivative. To go up levels, you're doing the integral. So if I go from a rate and I take an integral, I'm going to be at the amount. So this is the amount of leaves that the koalas have eaten. This would be billions of grams. So koalas in Australia consumed approximately 4.161 billion grams of leaves. And then let's think about what the 5 and the 7 represent. So we measured starting in 2015. So T would be 0 in 2015. If T is 5, we're talking about 2020. So we're going from 2020 to 2022. So this would be the context of the problem, the amount that they have consumed. When I integrate a rate, I get an amount. All right, hope this was helpful. Have a great day.